Well, I think we can get started again. Oh, we need Patty, though. Take your time, it's okay. Section 2B in the binder. Don't rush, Patty, it's fine.
We're trying to replenish our binder.
I'm
So
just,
it's the slide set is actually follow what I
Yes.
had before.
I
But
was
the
misled by Lauren. Yeah, you're right.
find your slide. Okay, so our next section, moving on, Dr. Dimitri Panagopoulos is going to talk about modeling and emission characterization from LBNL.
Thank you, Patty. So from my understanding, exposure is the star of the show, so to speak. And I think that that came up in the conversation with the panel and in the very nice introduction that Patty did. But what I hope to argue here is that in order to understand exposure, we need to understand first the properties of the chemicals that we're dealing with and the environmental fate of these chemicals in these fields. So my role in this project was to study the environmental fate of the organic chemicals released from synthetic turf by combining measurements and modeling calculations. So a small introduction about modeling. Modeling is basically a very simplistic approach where we just view the environment as one box consisting of smaller boxes such as air, soil, water, sediment. And we look at the fluxes of the chemicals between these boxes. The model works in a way that describes the environmental fate of a chemical based on the chemical's physicochemical properties and the properties of the environmental compartments. Two of the most common approaches are the approach of chemical potential and the approach of fugacity. In our calculations, we used the approach of fugacity as it was introduced by Mackay. So basically, fugacity is the partial pressure of a chemical in a certain compartment or the tendency of the chemical to leave a certain compartment. Fugacity is related to the concentration of the chemical via the fugacity capacity. So for those that have more of an engineering background, you can think of fugacity capacity as the relative humidity and the capacity of the air to hold a certain amount of humidity. So usually models are built on 4 levels, starting from level 1, which is a very simple and abstract approach, which is a closed system, steady state, and equilibrium. Steady state meaning that the emissions are constant, equilibrium meaning that the tendency of the chemical to leave all these compartments is equal in all these compartments, so the fugacities are equal. Level 2, more of a realistic approach. You have an open system where the chemical can flow in and out, but it's still steady state and equilibrium. Level 3, increasing complexity. It's an open system where you have chemical processes such as advection, reaction. It's a steady state, but the system now it's not at equilibrium. And level 4, we add another dimension to the system, usually time, and that makes the system not steady state, non-equilibrium. So the question here is, how do we apply the fugacity approach on the soccer field? How can we model such an environment in order to get to the exposure later on? So our approach, our suggested approach would be to basically divide the environment into several compartments. We know that already the turf is divided in several compartments. You have the turf fiber, you have the infill material, you have the backing layers, you have drainage stones. So what if we try to divide also the air into an upper air compartment, a lower air compartment, which will probably be close to breathing height. Upper air compartment can be about 300 feet above that. Then we can have an upper turf layer, a lower turf, and then the backing or the soil, whatever is under the lower turf. Now that approach allows us to adjust for differences in temperature in the upper and lower turfs, and for differences in the properties of the turf and the soil or the backing material. So by bringing all these compartments together, we can start looking at what are the emissions to these compartments, or what is the initial concentration of the chemicals in these compartments, what are the background concentrations that may be coming from surrounding areas, how much of the chemical is degraded in the air or in the turf, and how much of that chemical is removed from the system by migrating to lower levels of soil. So what do we know so far? We know that there are a few European studies that have tried to examine and try to make an assessment of the exposure and the risks. We know that they have identified several chemical structures. They have reported concentrations in air, particles, and turf. But then as the panel also pointed out, have we really covered the whole range of the chemicals that are in the crumb? And what are their physicochemical properties? What do these chemicals have for emission rates? How much are they released? They may be found in the crumb, but what if they stay there and they're not released to the air? How are these emission rates affected by environmental factors such as temperature, rainfall, sunlight? And what does that mean in terms of behavior? How do these chemicals behave in outdoor and indoor environments? And how does that in the end link to human exposure? So to answer the first questions, we recreated a section of the turf, which included the grass blades and the backing material and the crumb rubber. We used about 300 grams of crumb rubber, and our calculations were based on how much crumb is usually used in soccer field applications, based on previous reports from the Norwegian Institute for Air Research. So we took that section and we placed it inside the chamber that Randy was talking about before me. And we measured the emission rates of the chemicals released from the turf section to the air, and how these emission rates change over time. We used a standard chamber method, which is based on California specification. The chamber conditions were ambient temperature, 25 degrees Celsius, relative humidity 50%. The resting time of the air was about 10 minutes. You can see how the system works there. You have dry air, you have humidified air, mixing, getting into the chamber, and the chamber is basically located inside an incubator to maintain constant temperature. And on the chambers we have outlet and sampling ports and inlet where the air is coming in. The air is coming in and hitting the back end of the chamber, creating a good vortex of air inside the chamber, so the air inside the chamber is well mixed. For the sample collection, we collected air samples after time 0, 2, 4, and 6 weeks of incubation. We took samples for VOCs and for aldehydes and ketones at different volumes. Lower volumes for the VOCs, higher volumes for the aldehydes. You can see in the pictures on the right how the sampling cartridges look like for the VOCs and for the aldehydes. For the VOCs, we followed the sampling with thermal desorption and GCMS, and for the aldehydes, we analyzed the samples with HPLC. So these are some preliminary results from the emission chambers. These are the emission factors for the equivalent black chamber, which will be just the tray, the aluminum tray inside the chamber. So no turf, no crumb. The emission factor is presented in units of micrograms per hour per cubic meter, per square meter. So you can see when there's nothing in the chamber, we have low emission factors of some siloxanes, a little bit of acetone, some toluene, heptane, benzenes. And then as we incrementally increase the amount of material, now we have the tray and just the blades. So we see what chemicals are released from the blades. We see a little bit more siloxanes, some xylenes, and some benzyl aldehydes. And now you can see how many chemicals are released from the crumb when we introduce crumb to the chamber. And the magnitude of these emission factors is several log units higher than the ones that we saw from the turf or in the blanks. You don't have to read all these chemicals. They're just ordered from highest to lowest based on their emission factors. What I just wanted to show here is how these emission rates change over time. So if we go back to time 0 and we adjust our concentrations for the concentrations found in the blanks, you see that after 2 weeks, we have lower emission factors for many of the chemicals. Some of them remain relatively constant, such as benzothiazole. This is 4 weeks. Similar pattern here, benzothiazole is still constant. And 6 weeks. Now, if we focus our attention to, let's say, 1, 2, 3, 4 chemicals here, so if we look at methyl isobutyl ketone, p-xylene, benzothiazole, and naphthalene, we see that for the first 2 chemicals, the emission factor decreases really rapidly after 2 weeks. For naphthalene, it seems to decrease a little bit, but then it remains the same. And for benzothiazole, based on the measurements that we have up until now, we can say that the concentrations increase. We really don't know the reason, but for the results that we have, this seems to be the case. Now moving to the data for the aldehydes and ketones, again, the same principle. I'm going to show what is coming just from the aluminum trays that we have in the chambers. You can see a little bit of formaldehyde, alkyline, acetone, hexaldehyde. This is what comes from the blades. And this is what comes from the crumb. Again, the emission factors for the crumb are several log units higher than what's coming out of the blades. And as we did before, now I'm adjusting the concentrations for what's in the blank, and I'm going to show you how these concentrations change over time. So time 0, time 2 weeks, time 4 weeks, and time 6 weeks. Similar cases here. We don't really see a steady increase for any of the substances, but we see that, for example, formaldehyde seems to remain stable. We see that M-tolualdehyde is decreasing in the first 2 weeks and then remains stable. And for acetaldehyde, a similar pattern with a smaller decrease in the first 2 weeks. So what we aim to do after that is to continue to study how these emission rates change by exposing our trays that we reconstructed to cycles of high temperature and rain and some sunlight simulation. We aim to do that using a weatherometer, which simulates weather conditions in the real environment. And then we will measure the concentrations of the chemicals in the air above the sample to calculate emission rates and compare those emission rates to those that we have from the ambient measurements. So now from our data, if we go back to these substances that I talked in the beginning, these 4 VOCs, I'm going to show you some preliminary modeling calculations based on a model that we built to describe the fate of the chemicals in outdoor soccer fields. So now we're going to see the effect of activity, which is represented as particle resuspension in the field. So what happens when you have players playing in the field? How does that affect the concentration in the air? So as you can see, for methyl isobutyl ketone and p-xylene, the concentrations increase slightly with increasing activity. And for benzothiosyl, they increase a lot. The reason is because their starting point is different. And if we have a look at the different vapor pressures or the different log K octanol air, you see that these 2 substances are volatile enough to be found in the air without any activity. But for benzothiosyl and naphthalene, the concentrations without activity are very low, nearly 0, not exactly 0, but nearly 0. And basically, activity is the driving force for these substances in the air. Similarly, we looked at the effect of temperature, how temperature, surface temperature, how can that affect the concentrations of the chemicals in the air. We can see, again, we have a steady increase for all of these chemicals from 5 Celsius to 90 Celsius. So 5 Celsius, I guess, is about 10 Fahrenheit or 20 Fahrenheit. And 90 Celsius, you can boil an egg in there. So what happens then if it starts raining and the fracture of water in the crumb increases? Now, these are the calculations for a very dry crumb, with the fraction of water in the crumb being 0.001. This is what happens when you increase to 1%, to 10%, and to 20%. So for the different chemicals, the effect of the fraction of water in the crumb seems to be different. That is because of their different properties, their affinity for the crumb or their solubility in water. And what that can tell us is that, in dry conditions and in high temperature and where there's activity on the turf, the exposures are going to be really high. That's where they can be expected to be really high. So from these data, our next step would be to link a model that we created to describe the environmental fate of these chemicals in the soccer field to another model that describes how these chemicals are taken up by a human body, how a player can be exposed, and how long time will it take for these chemicals to be absorbed and removed from a player's body. And there's been a previous study recently published by Webster and Mackay, and in there they have a lot of references in the work of Debbie Bennett and Tom McCone, 2 of the most prominent Jedis of environmental modeling. And hopefully that will give us some answers to exposure.
Thank you, Dimitri. So we're at another discussion point. And I guess I'll start off by asking the panel any general comments at this point. Amy.
I just want to make a comment for the audience in case you couldn't see the scale, that the early graphs were in what's called a log scale, which is a whole order of magnitude for each level. So it starts at 1, but then the next one goes at 10, and the next one is 100, and the next one's 1,000. So those differences are very large. Then these later graphs are just arithmetic, and so the scale stays the same. And it wasn't probably that easy to see the numbers, so I'm just want to, he referred to them as logarithmic units, but it's also an order of magnitude. It's basically the same thing. And so just be aware when you're looking at these graphs that some of them are very different from others. So I just wanted to say that for the audience in case they couldn't see that.
Could you go back to one of them?
Absolutely. Yep. Yep. Yeah. Right.
So, Ed, a general comment?
So two general questions. One is you started off by describing sort of the physical boundary conditions of your whole assumptions, and you talked about this well-mixed sort of reactor. So is that assumption of a well-mixed and sort of the residence time that you built the whole model around, is that validated by making measurements outside and sort of looking to see?
So our idea here is to basically use the chamber measurements to calculate, basically build a model specifically for the chambers, and using that model to calculate the fugacity capacity of the material. So once we get that number, then we can take that and basically project those emission factors to an outdoors field, because the fugacity capacity of the material will be the same in the chamber and in the field, but the scale in the air above the field and compared to that in the chamber will be very different. So to answer your question, we're not really there yet, but there's an idea how to translate those emission factors that we measure in the chamber to emission factors in the field, and also back check with our field measurements.
Okay. And then the second question I have is with regard to this is actually a very elegant model and description, sort of looking at the steps, but the next issue or an issue looking downstream is the physical impaction of a step on the field.
Yes.
And so do you have in mind a plan to look at, some impact at different, pressures or to try and get some idea of what the resulting changes in concentrations might be?
Yes, we have, as Randy's going to explain a bit later, we have some preliminary results from field studies, from a field study, and in there we collected particles in the air, and we applied energy on the field to generate particles, and that will give us a very good insight on how that system works in real conditions, and if we can use those numbers to calibrate our model so that they describe a more realistic scenario. So if, for example, the concentration of the particles in the air is X, then we can take that value and
Right. I'm not just talking, though, about the concentration, the number concentration of particles, so I'm talking about gas concentration.
Oh, the gas concentration. Yeah. That's exactly. It's also something that we have to look into. Basically, by disturbing the thin air layer on the top surface of the crumb, because you impact the crumb there. Then, I think the field studies will be our point of reference, and we will calibrate the model based on the results that we get from the field studies.
Dr. Sheldon?
This is very, very nice work. It does have to do with volatile organics, and it does, sort of assume that, the unbound chemical is going to be one of the major exposure pathways. And how do you have any plans for how to figure out how important the volatilized component is relative to the component absorbed onto the tire crumb, and that is the major vehicle of exposure as opposed to the air? I know that's a lot more complex.
Yeah.
But I mean, but the key is that which one is most important to begin with, and then how do you address it?
Yes. So just to make clear that the simulations that I presented, the modeling simulations about concentrations in the air, that is the bulk air that includes both particles and what is dissolved in the gas phase. We haven't really looked so much into detail, but we're getting there into distinguishing between what's in the gas phase and what we absorb to the particles.
So when you modeled, actually you are also modeling upon impact the
Yes.
particles going up into the air. And, oh, you are?
Yes.
Oh,
So
great.
that we have
And
certain,
then you're modeling how much of it is inhaled or what could stick to the skin.
exactly.
Oh,
yes.
cool. Okay.
Yeah.
Dr. Bennett.
And then when you're doing these resuspension estimations, how are you getting the size distribution of the particles?
That is an excellent point. We don't really have any theoretical number yet because we don't really have any data from the crumb fields, but in our field studies, we sample for different fractions of particles. So hopefully there we'll see what impact on the field, what kind of particles it generates, and by looking at the different distributions, we'll hopefully be able to parameterize the model to describe that and say that, you know, in the air you have particles of PM10 and 2.5, but the particles PM10 will be deposited really quickly back to the crumb, and it will be the 2.5 that will be inhaled by the players, and these are the most important ones. So hopefully, again, the field study is going to give us some insight on what these distributions of the particles look like and how we can calibrate the model based on these measurements.
And then I had one other question. In the weather chamber, is there any possibility, I know that you've got the sunlight to try and make it more realistic, but is there any way to throw some ozone in there as well, or would that change anything?
Took the words right out of my mouth there.
Well, that's okay. Ed already stole my idea about the interaction.
Randy can talk a little bit more about the chamber.
So we don't actually own that chamber, so we probably can't put ozone into that chamber because there's a lot of plastics and stuff involved. But the material that we treat in the chamber is going to cycle back through the exposure chambers that we used. And in those, we can put ozone in because they're a completely inert system. And we have in past published papers with ozone injected into surfaces and looking at the chemistry inside those small chambers. So we will do the ozone experiment in those small chambers. The aging will take place in the weatherometer.
Dr. McCone?
My fugacity saber is a bit rusty, but he knows what I'm getting at. So I had a couple of comments. I mean, again, I think it's very interesting. I guess I can't really disagree with the approach. One of the things that I had a question about is when you see increasing concentrations, it could be a number of factors, one of which is transformation of one species to another, or it might be something else. And I was wondering if, you know, if it is a transformation of one chemical to another, the shape of the curve might go one way as opposed to if it's physical factors that are just altering the availability. And you might want to just look at the shape of the curve you see for the ingrowth or the rise of concentration. Again, it's just a thought. I don't know if that works, but there's a certain characteristic shape to a curve if something is ingrowing from a transformation of another substance. Then the other point is, I mean, since you know the near field fugacity, in a way you have the capacity or the capability of doing that. Humans are like just little lipid-coated objects moving around, and I mean this has been done before, right? Yeah. Well, just one. I mean, if you're a chemical, that's right. But you know, I know that this has been done for plants, right? Where you look at resuspension of particles, deposition on the cuticle of the plant, lipid surfaces. I mean, it might be interesting to put it in. And the reason I think it's interesting is that I've seen this mistake made several times that people assume that the only way to get things on your skin is to touch a surface, but actually when you're in an environment, the air is at a certain chemical potential, the carpet is, and if you're moving around, or indoors, but I mean, you're not chemically decoupled from an environment just because you're not touching it, right? And this is true for semi-volatiles and volatiles. So it might be an interesting, at least analytical experiment to just take, because we know the fugacity, and we can calculate fugacity capacity of skin and just say, okay, what would it be if the person got to like 90% of equilibrium, and how long that would take.
Excellent point. Thank you very much.
Dr. Kyle?
This is just a question on the implications of what you show here. And I might be asking it in the wrong part of the agenda. So if so, we can move it. But, 25 degrees is 77 degrees, and 40 degrees is 104 degrees. Right?
Yeah.
And I looked it up myself. I didn't calculate it. And it seems like these graphs diverge between 25 and 40. In other words, and so I'm wondering if that's a modeling artifact. And if not, it would suggest, back to I think Linda's point earlier, that maybe instead of looking at 25, you might look a little higher when you're doing some of these things to be more relevant to the field conditions, maybe. So I'm just asking because I noticed that, and I was just wondering. If
You were talking about these graphs here, right?
Well, I was looking at the ones that had multiple colors on them, but that where you're plotting the different water fractions.
Oh, right. Yeah.
Yes, those. And see, they're all about the same up until someplace between 25 and 40. So it just made me wonder if there's something important about those temperature differences that might make you think that 25 maybe is a little too low, and maybe you should be at 35 or something. So it's just a question or a comment maybe to consider at some point.
Yeah. I think, I think that might be because basically to adjust for the temperature, we look at the enthalpies of phase change for each chemical, and that's an exponential function. So I'm thinking that the temperature will increase more towards the end of the curve.
So it's a modeling artifact.
Well, it's based on real measurements. I don't think it's a modeling artifact. It has more to do with the chemicals' physicochemical properties, and hopefully also the field studies will give us some insight on how the chamber experiments will tell us more about how these enthalpies look like. How does temperature affect the desorption of the chemical from the crumb to the air, and we can adjust for that. These are just simulations based on literature data, but experimental data.
Well, I have a couple other questions that staff were concerned about, wanting to get panel advice. So one of these questions is partition coefficients and chemical diffusion properties are not readily available for crumb rubber. Do we have any recommendations for approximating these parameters? Turn to my modeling friends in particular.
Randy's not me.
Sorry, I was thinking. Even if chemical properties aren't readily available, there are ways of at least narrowing them down, quantitative structure activity, other chemical structure type methods. I mean, there are going to be questions about how reliable those are, but, there's a way to get a sense of how reliable they are. So it's possible. So you don't have to have measured chemical properties, and often the problem with chemical properties is what temperature are they measured at, and some of the estimation methods at least allow you to incorporate temperature differences, especially for vapor pressure. But
Dr. Bennett?
Yeah, I agree with Tom on the temperature thing, but also I feel like the diffusion coefficient values might not be all that relevant simply because of the fact that you've got kids running around on the field, and so it's not like we think of just normal diffusion. It's more advective as well.
Another question that staff wanted our advice on is, I'll just read it. As part of measuring emission factors for, excuse me, this is the one I didn't want to read that one. Does the panel have comments or suggestion for improvement regarding the compartments used in the model? The environmental compartments were based on differences in composition and transport processes. In other words, temperature gradient and crumb, difference in air transport, upper air and surface air. So going back to the slide with the compartment models, any suggestions, or do we think the staff have it nailed? Staff and their research colleagues.
I just had a question actually on that, because they had the backing or soil at the bottom and then it showed leaching down into the deep solid, but when they showed the picture of the actual product, it looked like there was this kind of drainage board underneath, and I wasn't entirely sure chemicals could go in or out of that or what that was made of. It almost looked like it was a hard bottom and we just had water loss, or I wasn't quite sure how they were handling that, the lower side.
Yeah, so this is basically just a suggestion. I don't really know if there's, if the picture that we show there, it's a golden standard for turf applications. I don't know if all turfs are designed in the same way, I guess, in similar ways, but that'll be something to look into. We can lock that department out if it turns out that this drainage stone is impermeable, then we just lock it and we focus on the layers above that.
And then the other comment I had too, just looking at this whole system in terms of the temperatures, because I'm just curious, normally when we have soil, the soil kind of absorbs the temperature down, and I'm just worried about how easily heat can diffuse through the system. So when we do have a hot day, how hot are we getting on the top? Because I'm concerned the heat doesn't diffuse into the ground as well as it does with soil, and so that would influence the temperatures we were doing any of these emissions for.
Yeah, basically that's exactly the reason why we want to parameterize the turf compartment as much as possible, so that we can isolate the upper turf, which is mostly impacted by temperature changes, as opposed to lower turf and back in soil where the temperatures are more constant. So you may have 50 or 60 degrees Celsius in the upper turf and only 25 in the lower and 10 in the soil. And our model allows for different temperatures in the different compartments. So that's the idea there.
Tom?
How big is your upper air?
So, the upper air suggestion now, it's about 300 feet.
Is there? I'm wondering if there's any need for, and the reason I ask is, so you got an air layer way up here, right? Anything that gets in this model system, anything there is never going to get back to the soil.
Exactly.
Almost the probability of a return, which is all you really care about, is you're trying to balance, do a mass balance. And then I actually think in terms of air, that's a loss, anything that goes out. And you might want to put your lid even further down. And maybe use two. So I'd be interested in and again, you'd have to do this with some sort of sensitivity to figure out where to put the break points, but there's going to be a very stagnant air layer that might only be centimeters or just above. And that could be very important because that can be a reservoir. And then as you get above the field, there's going to be a little bit of turbulent mixing, but still these two may communicate. And I think that next layer may only be like 2 meters.
2 meters, okay. Yeah.
I mean, something though, because if you look at, and again, I don't know off the top of my head, but there's a real rapid increase in the velocity of air and the eddy currents and the diffusion, mixing. So you get a lot of mixing, and the more mixing you get, the more it's going to just vent off. but you want to kind of capture where there's a trap. And also for exposure, that low layer, I mean, when people are laying on the ground, like breathing, they're in this like vapor zone, or they're in a much higher concentration zone, maybe in the first, and I don't quite know what the number would be, but a very thin layer. And then the next layer would be the upper breathing zone. And then beyond that, things are really going to get vented off. But this could be structured with like a sensitivity analysis to see what the losses are. Because the wind velocity is essentially zero at the ground. I mean, and then makes a transition to the 10-meter wind velocity, and then rises from there. But these change very dramatically because there's a very rapid, especially if you look at that picture, this is not a forest or anything. This is a flat surface. So as the wind goes across, it's going to have this really classic movement from stagnant, laminar, right, nice smooth flow, to
Turbulent.
steady, turbulent layer, and that's all going to happen in 10 meters. And again, I'm just approximating, but you might want to explore that because that'll make the model, a lot tighter for them.
Excellent. Thank you so much.
So we've talked about elevated temperature, elevated ozone, possibly rain events in simulating the aging process. So I'm just asking the panel, are there any other environmental factors that should be considered?
I think also sometimes don't they apply water to the field just to deal with the heat of the field and to prevent things from stirring up, although that's kind of like rain. Or on a hot day rather than...
Right, I hear you. Okay, any other comments before we move to the next section? Good, thank you.